What you're looking at right here is the first 84-volt Gotway Nikola that was ordered from Jason at eWheels in that first batch that had come in. And I guess the first question might be asked is, why is this wheel sitting here on the bench, semi-disassembled? And there's a pretty easy answer for that. This wheel currently has about 90 miles on it, and it was ridden until last week. And then an interesting incident happened where a popular poster on the forums and a long-term electric unicycle rider by the name of Marty Back was doing a stress test on an 84-volt Nikola, and basically the control board vaporized. So at that point, after doing a little bit of reverse engineering on what had happened there, a little failure analysis, it was determined that the MOSFETs, two of the MOSFETs had burned up, which appeared to be due to a contaminant between the MOSFET and the heatsink, which is, of course, a very important thing for high current devices such as this. When looking at those pictures, as soon as I saw the photos of this, it struck me, being a guy that's in electronic manufacturing and design, that this looked like it was a case of creative assembly, where sometimes on production lines, production workers will find a quote-unquote better way to do an assembly job. And in this particular case, it looked as if some type of adhesive was used to aid the assembly process when assembling the motherboard or the control board onto the aluminum heatsink. So from that standpoint, after I saw those pictures, I parked my Nikola, which was a pretty sad thing because this is truly a wonderful wheel. I'm blessed with many other wheels to ride, but I was really very much enjoying this wheel. To give you an idea of my usage of this, in my 90 miles of it, I was pretty much riding it around suburban rolling hills, very small amounts of dirt riding. And so this wheel has not lived a very stressful life. Speeds were reasonably brisk. 25 to 27 miles per hour, probably at the top end. Rides were generally about 20 miles at a time. But like I say, nothing I could say wrong about this wheel. And before taking the cover off this wheel and putting it up on the bench here, this wheel has performed flawlessly. However, seeing that there's a possibility that there might be a very serious lingering problem on this board, I thought it would be prudent to go disassemble this, pull the board out, and take a look at what an operational Nikola from this same batch looks like. Now, the hope would be it will look somewhat different than the ones that had the glue underneath between the MOSFETs and the heat sinks, but better safe than sorry. So at that point, that's why we're here today. So enough with this. I'm going to go and pull this board out. You can see I've already done some disassembly on this to save a little time on this video. These steps are documented elsewhere, so we won't go into detail on that. So at this point now, we are ready to lift this up and take a look at what's underneath it. As we can see down here, this little pad that's under there, this is a thermal silicon pad that is used to transfer heat from the tabs of the MOSFET into the heatsink. And the idea of this is that under compression, it fills in the air gaps between the metal, the rough surfaces of the metal, of the aluminum, and the tab of the MOSFET package, in this case a TO220. In a future video, I'll discuss some other ways this could have been done and ways these Nikola control boards can be improved. But at the moment, we'll just take a look to see what we're out there to find out whether this board would have blown up at one point or another. So here we go, and I'll get a better camera angle once we see. But this should be the big reveal right here. Okay. So what we see, which is what we had seen previously, is the top row of MOSFETs, the ones that were on the edge, had the barrier on them but were not attached by any type of material. So this looks like a good connection, in so much as the capability of this thermal barrier is able to deliver. This looks like this was a pretty good job. So the next step. Now I'm seeing something I don't really like here. I'm going to take a little closer look, and I'll probably get. Yeah, this is not good. What we see down on the aluminum here is I'm looking at a substance down on the heatsink itself, and I'm going to take a better shot of this for you. That looks like hot glue. So it looks like there was some hot glue down on this stuff. The contaminant creates just as much problem if it's on the aluminum surface than if it's directly on the pad. However, it may be okay in this case because it's more toward the center here, and I'm not sure it actually hits the pad. But let's take a look to see what's underneath the pad just to get an idea. Because this is where the problem had shown up in other boards. Oh boy. No, this is not good. This is not good. So at this point, we've determined that the thermal pads on this fully functional Gotway Nikola were assembled using adhesive. Now, this particular wheel, just to note, basically had no anomalies whatsoever, was working fine. So it's interesting to see how this worked. There's no signs of heat damage on this board. So we did quite a bit of work in examining the surface of this board. If we look carefully here, these are the affected MOSFETs, these two that we're looking at right in the middle here. And there was actually some contaminant also on these others, but these are the two historically we've seen that had problems. Now, interestingly enough, when we actually examined this closely, I was surprised to find out that actually there was no glue present on the metal surface of these tabs whatsoever. This was completely clean. I could take an ohmmeter on this and demonstrate that this is just bare metal. And in the close-up macro that I'm putting up on screen, you can see that there's almost like a cutout around that glue surface. I do not believe that this was done with a template. It looks to me as if this was a squeeze out, that this material was very runny, and when it was tightened up, it looked like the glue squeezed out. There's also no sign of glue remnants on the pad itself, although it is possible it absorbed it in some way. I don't know. But anyway, from this standpoint, it would appear that if there was anything blocking the heat transfer from this MOSFET into the pad and thereby into the heatsink, it was a very, very thin coating, and that's possibly why this board had no problems up to this point. So at this point, I'm fairly convinced that these MOSFETs have not suffered heat damage. So I'm planning on putting this board back together. The question would come up, what am I going to do about these heat pads on there? I mean, obviously the options are putting a pad solution similar to what we've seen already with those heat pads on the side. I think it would be rather difficult to assemble that without some type of a jig, but I think I would know how to do that anyway. And then there are certain other commercially available products we can use to do a good thermal coupling from these MOSFETs into the board. So at this point, I'm just going to go off into a little science fair experiment into how these various materials will work, and particularly using the actual heatsink that was installed on the Gotway. And at that point, we're just going to have a little fun with this. This is, as a science fair experiment, it's probably not going to be that good. Probably the 7th grader at the table next to us that is demonstrating that increasing the population of frogs would prevent catastrophic climate change would probably win the contest over us. But we'll do the best we can and get into it. Well, for our first thermal test, we're going to do something which is kind of like a control for this experiment. So I have a soldering iron with a chisel tip here, a wide tip. Just put it in frame so you get an idea what that looks like. And what I'm going to do is I'm actually taking a TO220 package, which is identical in configuration to the one that's installed on the Gotway Nikola. And in this particular case, this part is not a MOSFET, it's a voltage regulator, but what we're really looking at is the thermal characteristics of the package, not the function of the die that's inside the package. So I'm not imagining that there would be any difference if we were using, you know, the high MOSFET that is actually used there. So in order to do this test, what we're going to actually do is I'm going to set a timer, and I'm going to apply the I'm going to apply the soldering iron to the leads of this. In this case, I have this lying on just a junk PC board that is just being used as a substrate, and hopefully something that's not terribly conductive. So this is exactly what you wouldn't want to do if you were putting a MOSFET in an electric unicycle. So in order to start this, what I'm going to do is I'm going to start this timer. I'm going to go for 50 seconds, and we're going to get an idea of basically how hot that heatsink tab and the body of the device gets in that period of time. Now this is a very informal test, but it gives us a basic idea of the types of things that a heatsink can provide to us. So let's get started with this test. So I neglected to say that this started out at basically room temperature when we started it. And try to get this in focus a little bit better. It should be good. We have to get pretty close in here so we're not measuring the temperature of the board too much. Looks like a good angle there. So we can see we're getting a climb of this temperature. This is 27, 29 seconds. Starting to get a pretty substantial climb here. And I'm going to go a little bit longer on this, but what we're seeing now, I'm going to go to about a minute here, and we're seeing that we've actually gotten quite a bit of climb here. We're going up to 127, 128, so we're kind of in a place here, up even a little bit more, so I'm going to release this on there. So we can kind of feel that by the time we get past a minute, we're getting rather hot on this device. So this gives us an idea basically of what can happen. In this case, the soldering iron is applying temperature directly to the device. In actual use, the actual impedance of the device would be consuming power, and at that point, that would cause the heating of the die, which would then radiate out to the case, and hopefully would be shunted off into the heatsink. So now let's move on to another test. Well, for this next test, I'm going to mount the TO220 package directly to the Gotway Nikola heatsink using the original pad that came with my Nikola that will be attached using the original hardware. Now, if you see the TO220 package on the left, to the right of that, this is the hardware that was used to attach it into the heatsink, and we can see a very typical setup where there's an insulating sleeve or collar that goes down into the body of the MOSFET, and in this case there are two washers that are on top of that, on top of the little bolt that goes down into the heatsink. So I'm going to be attaching it that way. As we said, we've just now mounted the package that's simulating the MOSFET onto the board that's torqued down pretty good onto the pad, mates up really nicely. Now you see I have that I have a piece of PC board next to the leads, which is just really meant to be a thermal insulator so that I wouldn't be pressing the leads directly down onto the heatsink, which would skew the test. So in this case, that should make a pretty decent thermal insulator and not mess things up. But of course, I'm going to do the following tests after this in exactly the same way. The previous one with freestanding was a little bit different because there wasn't a nice solid attachment point. But for this, basically, we should be in pretty good shape. So I'm going to run this for about a minute. and we'll take a look what the temperatures do. Okay, get some pressure in there, and we're going to start up the stopwatch. Now, in the meantime, I'm going to go sneak in with the heat probe. Try to get an angle so you can get a view of it. And you see we're starting to get a little bit of temperature elevation there. The nature of these heat solutions is that the larger temperature differential there is between the heatsink and the part, the more efficient the heat transfer is. But that's just the nature of heat. Getting quite a substantial climb here. Clearly we're doing quite a bit better than we were doing previously. Also going to try to move the probe around. By the way, this is not the most accurate way to do this. It's just kind of convenient, quick lab reference. If we actually, mounted a temperature device on top of the part, we could get a much better reading than this. So I'm at 110. I'm going to run this to 130, and we'll get an idea because we're still only about 60 degrees. See, 67. So this is obviously doing something, this heatsink, which is nice to see. So at 130, we're at about 64 degrees C. So we're not in any way in this test attempting to simulate what's actually happening in the wheel. We're just trying to get a general idea of how good this thermal treatment that Gotway put on this wheel is. And we can certainly see that it's doing something, and that's a reasonable amount of heat that's being applied from this gun. So my feeling is it looks like it's working pretty well. So let's move on to another test. So for this next test, we're going to try a different type of product. I'm going to try to zoom in a little bit here so you can get a better view of this. Better there. What this actually is a thermal pad, and these are products that we use quite a bit for just like informal cooling purposes. They're very easy to work with. Basically, they come in sheets that are pre-cut, and if you can see the sheet, I don't know whether it's going to be easy to see this or not, but you can kind of see there's holes pre-cut in the sheet, where the screw hole actually goes. Just point in with this over there on there, so you don't have to take that. That basically comes off with the sheet. So basically it's kind of peel and stick. It has an adhesive on it, but it's a very non-gooey adhesive. It's almost kind of like surface tension mount. So it's super easy to install. So then I've installed that on on the MOSFET, which you can kind of see here. I'm trying to keep in frame here in the camera. And we've installed this on there, and I'm now going to bolt this on in a similar fashion to what we did with the Gotway pad and take a look whether it works in a similar fashion. Okay, so now we have the thermal pad attached onto the back of the MOSFET, and the MOSFET is torqued down onto Gotway's Nikola heatsink. Once again, I'm using the piece of PC board over there as a bit of a thermal buffer and a platform to allow me to push down with some force with the iron to get heat into the junction. And once again, we're going to be using the infrared thermometer to try to get an indication of the temperatures that we're seeing on the device. I'm just going to slide this down a little bit closer. It's probably going to make it a little bit better angle. Make sure we can actually get in here and see this. Okay, and I'm trying to center this as much as possible on this. This device is actually a little small to use with this temperature probe, so I'm going to try to do the best, but I still think it gives us good information anyway. So at that point, the first stage is I'm just going to get ready to start the timer, and we're going to, okay, there we go, we got good coupling in there, and we've got the timer started, and I'm going to kind of sneak in there with the probe and get an idea of what we're looking at here. Okay, we can see we're starting to climb in temperature. Coming up to the 30-second mark here. Coming up on a minute. It's pretty soon. Trying to keep nice solid pressure down those leads to couple as much temperature as possible into the package. Seems to be working quite well here. We are putting a lot of thermal energy into this joint from this soldering iron. And I think we're going to end this at a minute 30 like we did before. Take a look with the iron is out there. And the temperature is dropping already. Look at how that temperature is diving. So anyway, this looks like this is working quite well. So we're going to move on to one more test. Well, for this next test, I thought we'd have a little bit of fun. Well, if any of this can be called fun. What you're looking at down there, lying down on the Gotway heatsink, are the remnants of the adhesive that I peeled off of the heatsink and from the MOSFETs of my Nikola. Now, for those that have been following this story, my Nikola ended up having no visible residue on the mating surfaces of the MOSFET itself, but it appeared that the liquid had squeezed out when the MOSFETs were installed, which seems a little scary. But on the other hand, the mating surfaces were fine, so I believe that my particular unit probably would have been quite healthy. So we see some of the other units that seem to have a substantial amount of this material under the surface of the MOSFETs. So I thought it would be fun if, since this stuff melts quite easily, if I put a little bit of that glue underneath one of these TO220 cases attached with the Gotway official thermal pads, and to get an idea, since we had a basic reading of what the thermal pad did in an uncontaminated environment, we'd have a basic idea of how much this degrades the performance. So I'm going to go and do a little melting, and I'll be right back. Well, try as I might, I just could not find any way to get that original Gotway adhesive to to coat the back of this the back of the MOSFET in a way I thought would be realistic. I could take pieces of it and glob it in there, but that's not going to be proving anything, because that's not really what happened on the wheels. So, because I did want to have some fun anyway, and I thought that would be fun, I decided to do something incredibly stupid. And so this is what we have here as incredibly stupid. What I've done basically is I've taken just a piece of Scotch tape, and I put a piece of Scotch tape there, on the mating surface of the MOSFET, and I'm now going to put this onto the original Gotway pad and just get an idea how much difference a piece of Scotch tape is. I've got the funny feeling that the Scotch tape's probably not going to be all that much worse than the glue, but it's hard to say. You'd have to actually test the real thing, and I don't have a sample of Gotway's actual glue so I can do test on. So just for fun, let's try this and see how it works. I'm going to mount this up with the pad and do the test. Okay, so now we have the MOSFET attached to the heat sink using a piece of Scotch tape on the thermal tab, the Gotway thermal pad, and then at that point screwed into the heatsink with the other hardware, such as the the insulating collar around the mounting screw. So at this point, basically, I don't know exactly what this test is going to tell us, but on the other hand, I thought it would be fun to take a look, because it'd be interesting just to see exactly how sensitive to this is this system to small amounts of contamination, or at least with this very informal and probably very inaccurate test. So that being said, we're going to get ready to go, and I'm going to get the iron on the unit, and there we go on there. We're going to start the timer and take a look to see what happens with the temperature. I feel like this is almost like one of those overclocker tests, where they go in there and they put spaghetti sauce as thermal paste to see how well it works. Well, look at this, though. Isn't this kind of incredible? Look how fast this is climbing up. Wow. I'm a little shocked. Now, mind you, this doesn't indicate this would be the problem if we get with Gotway, but I think I'm going to end this test pretty soon, because look at this, we're at 30 seconds, and this has climbed up quite a bit. So that little piece of Scotch tape had a big difference. So that certainly does make us think a little bit more. Sorry, I'm having a little trouble keeping the probe pointed correctly. Yes, I'm going to stop this right here, because by the time we get to a minute, we are talking about a lot of temperature in there. So, this would kind of give me the basic feeling that maybe we probably should not be using Scotch tape as a thermal coupling. It also makes us suspect that relatively small levels of contamination between the MOSFET tab and the thermal pad could make a very significant difference. So I'm actually surprised at how much difference that makes. Not that it's a good idea, nor would I ever put it in a product that I design and manufacture, but on the other hand, sometimes you kind of feel that these things are, you know, a little bit closer to superstition than actual practice, and this would tend to make us feel that this is a really serious issue, which is kind of good in a way, because theoretically it's supposed to. Hi guys. Okay, I just wanted to summarize a little bit some of the tests we had just done. In terms of looking at the thermal performance of various types of coupling means onto the Gotway heatsink. I think there were some expected conclusions we can make out of this and some surprises. The first thing we could say basically is that my opinion is that when the MOSFET is attached properly without contamination through the Gotway supplied thermal pads to this rather massive and I think very nice heatsink, that the performance of it I feel is very good. I mean, basically with the massive amount of thermal energy we're putting in from that high temperature soldering iron. By the way, that soldering iron was about 750 degrees Fahrenheit. It was set out. We use that for installing big connectors, gigantic, massive things with a lot of thermal capacity. It had that big chisel tip for coupling in. Of course, the thermal capacity of the leads going into the package do limit a little bit how much energy goes in there, which is why we use pretty big temperature on that. But I think it's, I mean, is this a perfect test? Absolutely not. This is not a perfect test. And can we come up with a lot of things that are wrong with this test? Yes. We come up with many things that are wrong with the test. Does this give us a basic informal feeling as to how well these solutions work? I think it does. I think it does. So just a couple of notes I had on this. Basically, if we look at this, in my judgment, basically the Gotway pad in that particular test of 1 minute and 30 seconds with that iron on it, produced, I'm going to call it somewhere around 65 degrees centigrade. The final temperature on there, which, as we've seen in our original unsupported test, it's really almost unlimited how high that temperature would go without anything other than air cooling and non-moving air cooling on the tab. So basically, putting in these aftermarket tabs that we put in that we do use here. That the product, by the way, is an Avid. That's AAVID therm pad. For the TO220 package, and you can get that either with the tear-off self-adhesive or without any adhesive at all. The tear-off self-adhesive seems to work quite well, and it's super convenient. Assembly would not be a problem, or reassembly would not be a problem with with using those, because they stay in place. And you basically get the screws and the hardware through it and all. So without going into great detail. So we look at the performance of that packet. I'm actually calling that in my internal, like in my personal evaluation from what I'm seeing here, I think it works better than the Gotway pad. It's not terribly surprising, since it's probably a similar kind of material, this thermal impregnated silicone that is used quite a bit in those pads. That particular pad is quite a bit thinner than the Gotway pad, and I think possibly that might help its coupling a little bit. It is also, by the way, an electrically insulating pad, so no other solutions needed other than the pad directly, onto the aluminum heatsink. I would tend to call this about really 50 degrees C in that test, compared to about 65 for the for the original Gotway supplied, pad. So I think it actually is a little bit better. Now, mind you, these tests are wildly inaccurate. It's very, very difficult in the kind of the way I was doing this to try to keep the infrared probe pointed the right way and things of that sort. But informally, I would say that that solution works at least as well. I would suspect that in reality, with a more controlled test, it works quite a bit better. But nevertheless, I think they both basically get the job done. Now, that final test that we did, which was really just for fun, like I say, we were trying to get the glue on there. That didn't work. I was actually surprised how much, how much interference that little piece of Scotch tape made when we attached it to the back of the MOSFET. And basically, that that test, we called that off after the temperature elevated to about 150 to 170 degrees C. After a short period of time, less than a minute. So from that standpoint, that's just an indication that putting a little bit of contamination on there makes this thermal solution not work at all. This might feed into the theory that if the glue layer is anything but really microscopically thin, which it appears to be on my board when I tore it down, if there actually is any of that glue that ends up being globbed under there, you're probably going to have a serious thermal problem on the MOSFETs that are affected by that. The units we've seen so far, the effect actually has been that the MOSFETs that have glue on both MOSFETs that are working together in a pair are the ones that have blown out. The other ones where there was glue on one MOSFET, the load was most probably taken by the other MOSFET. Another thing to look at in terms of the glue being implicated in this is that it's the nature of BLDC three-wire motor connections. What's called star configuration. That at any point, basically, out of the 3 wires going to that motor, one is being pulled up by a pair of MOSFETs because we're working in pairs with this wheel, and there's another wire that's being pulled down by MOSFETs in the other bank. So a curious thing basically is that the current that's being supported by that one MOSFET, the one MOSFET pair that burned out, was also being supported without any damage by another pair of MOSFETs in the other bank. So, is this definitive? No, but it's kind of what's different about the other bank? No glue. So I think it's definitely something to think about, not actually definite. I'm going to call this video short at this point, and basically, the next video in in this pair, basically, I'm going to show you one more thermal solution for coupling these MOSFETs up to this Gotway heat shield, and then I'm going to describe what I'm doing for my personal wheel, and I'm going to demonstrate how that's implemented and assembled. So until then, thanks for watching.